Hi, my name is Sasha Geller, and my study is identifying volumetric differences in the amygdala and its substructures correlated with menstrual cycle hormonal fluctuations. Women face double the risk for depression and anxiety compared to men. However, women have been excluded from neuroscience research due to perceived hormonal confounding despite higher disease burden and risk. This results in insufficient understanding of women's hormone brain relationships, with minimal understanding of hormone driven mood disorders that primarily affect women, like postpartum depression and premenstrual dysphoric disorder. So the amygdala plays a key structure in this. It is a bilateral structure, one in each hemisphere, responsible for emotional memory formation, stress response, and autonomic nervous system control. So Oswarty found that structural plasticity was associated with menstrual cycle hormonal changes, and that there was a high density of those hormone receptors in the amygdala. So Stevens and Hammond found that women have higher amygdala responses to negative stimuli compared to men, establishing sex differences. Aucklenberg found that amygdala structural asymmetry had been documented, but menstrual cycle effects were unknown. However, the menstrual cycle effects are present on the functional asymmetry shift. So, the amygdala is comprised of multiple complexes, which are groups of substructures. This image here is the two major amygdala complexes, the centromedial and basolateral complexes. So, the centromedial in the purple is primarily responsible for the output pathway, and it controls autonomic nervous system responses and arousal. It is primarily connected to the brain stem, while the basolateral, the pink here, is the input processing pathway and mediates cortical connections and emotional memory. So Peterson and Kyle found that different anatomical connections suggest different hormone sensitivities. Additionally, Oswarte, that same study, found the medial nucleus of the centromedial complex has many hormone receptors for the menstrual cycle hormones. So, speaking of menstrual cycle hormones, follicle stimulating hormone, FSH, is fluctuates significantly across the cycle and it peaks at ovulation. FSH stimulates the follicle development in ovaries, and FSH and its receptors have been found in the brain. And it, in 2024, Reiser and colleagues found significant correlations between FSH and cortical thickness, which was preliminary evidence that FSH has independent effects. So, the gap in the knowledge is that FSH has been completely ignored in neuroscience research in favor of estrogen and progesterone, causing key hormonal relationships to be missed. Additionally, studies treat the amygdala as a single structure and only examine functional asymmetry, causing any structural asymmetry and complex specific effects to be missed. So, this study addresses the gaps by both testing whether amygdala structural asymmetry is stable or dynamic, and examining whether the CEM and the BLA change in response to FSH. So the research aims are first to investigate amygdala structural asymmetry across cycle phases, like I said, because the relationship is currently unknown. Second is to correlate FSH levels with the centromedial and basolateral complex volumes, and to compare those possible volumetric shifts. They would be compared because, like I said before, the CEM and the BLA have very different functional roles and connectivity, and that may show different hormonal sensitivities. So I hypothesized first that the left-right volumetric asymmetry will vary across cycle phases. Second, that the CEM volume will show changes correlated to FSH changes, but the BLA will not show changes. It will remain stable. So this was tested using a secondary data analysis of an open source dataset by Reiser et al. In 2024. There were 20 subjects with 3 scans each, ages 18 to 30, all naturally cycling. There were blood hormone levels and T1 weighted MRIs, and the previous study was IRB approved. The analysis was done using a neuroimaging software, analysis software called FreeSurfer, and it segmented the amygdala and the centromedial and basolateral complexes, meaning it separated it so then I could do the statistical tests, which were linear mixed effects models. I use these because they work with the repeated measures design. My subject was an intra-subject design, meaning it compared each subject to themselves, holding itself constant to eliminate confounding variables like baseline anatomy and head size. So my study was the first to combine separating the CEM and BLA and correlating it to FSH across 3 cycle phases, not just 2 cycle phases, and using blood hormone verified cycle phases. So the first finding is stable leftward asymmetry of the whole amygdala. The left amygdala was shown to be about 2.7% larger than the right amygdala, and it was statistically significant with p equaling about 0.04. And it was stable across all cycle phases. This is a novel finding. So, asymmetry being stable across all cycle phases, challenging the hormonal confounding assumptions that have excluded women from research. So, the CEM and the BLA are showing distinct patterns in relation to FSH. This graph is showing the change in volume in response to the FSH levels. So, the BLA, this pink line, is showing no change, but the CEM is showing a negative trend, which is illustrating different complexes showing distinct patterns in relation to hormonal changes. So the final finding is the periovulatory phase is showing unique CEM FSH relationships. So the star is about the periovulatory phase because only the periovulatory phase shows a significant correlation. So the change, the beta was negative 0.86 millimeters cubed, meaning that the central medial lost 0.86 millimeters in volume. Um, and the p-value was about 0.006. This is a novel finding. This is the first study to identify phase-specific FSH effects on amygdala substructures. So the hypothesis evaluation. The first hypothesis was partially supported. Leftward amygdala asymmetry was confirmed, but it was stable across phases, and this provides evidence that hormonal confounding assumptions are false. The second hypothesis was partially supported. The CEM-FSH relationship was significant, but it was only in the periovulatory phase, and this reveals novel effects hidden by traditional research methods. Additionally, the final hypothesis was fully supported. The BLA had no correlation to FSH, and this supports complex-specific hormonal sensitivities. So the limitations were stem from a lack of publicly available menstrual cycle data, the first being small sample size, and in the future I would like to replicate with a larger sample to increase statistical power and generalizability. Second, that only FSH was examined. In the future, I would like to test the full menstrual cycle hormonal panel to determine if FSH effects are independent. The third is that there were only 3 discrete time points. In the future, I want to scan more frequently during the periovulatory phase in order to examine the CEM FSH relationship more precisely. So, the research implications men and women showed structural brain differences, but past research excluded women justified by hormonal confounding. This study shows that hormones are predictable, not confounding. These findings challenges assumptions that justified excluding women from key neuroscience research. So the clinical implications are that the normal hormone brain patterns established by this study could form the necessary foundation for identifying hormone-dependent mood disorder abnormalities. These novel findings advance both research methods and clinical understanding of women's hormone-brain relationships. This is my bibliography. Thank you for listening.